Today we're going to be talking about the Fundamental Theorem of Calculus Part 2. Now you might be asking yourself, well, Part 2, we haven't done Part 1 yet. Most books honestly do what our book calls Part 2 first, and they call that Part 1, and then what we're going to call Part 2, which is really Part 1 in our book, they do as the second part. But I think that explaining it, flipping them like I'm going to do, makes sense to you guys. Now, this slide here, okay, this should already look familiar. This is what we just did in the last day. Okay, so remember that this function, big f of x, is the antiderivative of our f of x, and you take and you evaluate the antiderivative at the top value minus the bottom value. So evaluate each using the fundamental theorem of calculus. Okay, so we've really already done this. So I find what the integral of that is. That's negative x to the negative 1. I evaluate from 1 to 2. I plug in 2 first, minus a negative x to the negative 1. So that's really a negative 1/2 plus, that should be a 1 in there. I'm trying to go through this super fast. Plus a 1, so that gets me a 1/2. What function's derivative is cosecant? Well, that's the negative cotangent. Cotangent, not cosine. The cotangent of theta. And I'm going to evaluate that from pi over 3 to pi over 6. So I'm going to actually pull out that negative, and I'm going to evaluate cotangent at pi over 3 minus the cotangent of pi over 6. And cotangent of pi over 3 is root 3 over 3 minus cotangent of pi over 6 is root 3. So I'm going to get my common denominator. So I have a negative 2 root 3 over 3. And that simplifies to get me regular 2 root 3 over 3. Okay, I went through that super fast. We've already done that. But remember, what I'm finding with each one of these is I'm finding the area to the x-axis. Okay, so that's really going to be our goal. So to find the area between a curve and the x-axis over an interval. Okay, and when they're saying find the area between the graph and the x-axis, that means you're not accounting for the positives or the negatives. Okay, so you find the zeros. You integrate over each subinterval and then take the absolute values. A lot of times they're going to be calling this the total area. So for example here, I want to find the total area of the region between the curve and the x-axis. Meaning, when I graph this curve, now look at what this curve looks like. I have a negative, I have an x that I can factor out. That's going to leave me with x plus 3. So my zeros are 0 and 3. And we know it's a parabola that faces down. What I'm looking for is I'm looking for this blue area plus this green area. Now the green area is positive. The blue area we know because it's below the x-axis is negative. But when I'm looking between the curve and the x-axis, that means that and it says the word total, that means that I have to think about this as a positive area. Okay, so let's worry about finding that green area first. So I'm going to find the integral from negative 3 to 0 of my function. Okay, so finding that area of that green, we have negative 1/3 x to the 3rd plus 3/2 x squared. I'm going to evaluate that from negative 3 to 0. When I plug in 0, I'm going to get a 0 minus, I have a negative 1/3 times by negative 3 cubed plus a 3/2 times by negative 3 squared. Now going through And evaluating all of that, I get 9/2. I'm not going to bore you guys with going through the algebra of that. You guys can do that algebra on your own. Now the other one, this area that's negative, I'm looking at the area from 0 to 1 now of our function. Don't forget your dx. I've already taken the integral of that. So I'm going to go from 1 to 0. Now plugging in, evaluating now this integral, plugging in 1, we get a negative 11/6. But remember, I need the total area, so I'm not going to think about that as a negative. So I'm going to take the absolute value of that, which is positive 11/6, add that to my 9/2, and get 19/3. So that's the total area between our curve and the x-axis. In this example, we need to find the area of the shaded region. Now notice how there's two functions that bound this region. There's one here that's y equals 2x squared, and then we have one over here to the right that's y equals 3 minus x. So what you want to do is you want to split this up where the two functions intersect, and you're going to find the area of region A and add it to the area of region B. So region A, we are taking the integral from 0 to 1 of the area underneath the curve of 2x squared dx. And we're going to add that to our region B, which it's starting at 1 and going to 3. And we have 3 minus x dx. So now it's just doing the math. Okay, so the integral of 2x squared is 2/3 x to the third from 0 to 1. We're going to add that to 3x minus 1/2 x squared from 1 to 3. I plug in 1, I get 2/3. Plug in 0, we get 0. Now I'm going to kind of do a little bit of math here so that I don't make mistakes. So I plug in 3, I get 9. I wanted to put that in parentheses. That was the math I was talking about. 9 minus 9/2 minus, when I plug in 1, we get 3 minus 1/2. I don't like working with fractions, so I'm going to hope, well, I don't need that parenthesis. I'm going to hope that some of the numbers in here kind of simplify. So I have 2/3 plus 9 minus 3. I have a negative 9/2. Looks like we have a plus a 1/2. So that simplifies to 2/3 plus, I have a 6 minus 8/2, which is 4. So I have a 2/3 plus 2. That gets me 8/3.